Chen from Michigan State University to tell us about a spherical group ring model for equivariant A theory.
All right. So thanks so much for coming, and thanks so much for the opportunity to speak. So like Yuchon said, the title is Spherical Group Ring Model for Equivariant A Theory. I'm not expecting that you know probably what most of these words mean, except maybe equivariant, but we'll sort of get to that. And this is all joint work with Maxine Calle, Anish Chedalavada, and Andres Mejia. All right. So I want to begin by sort of just talking broadly about algebraic K-theory. So this is an algebraic K-theory talk. And just a little bit of introduction about algebraic K-theory, and then I'm going to talk about applications to geometric topology. So what is algebraic K-theory? Well, it's a construction which at sort of the most basic level takes in a ring, and for every ring you get a spectrum, right? And we are allowed to sort of take our spectrum and abstract some groups out of it by taking homotopy groups, and we call these the K groups of the ring that we started with. And I want to just walk through an example to sort of get a sense for what these things look like and sort of talk about what they do. So of course, the example I want to start with is we're going to take R to be a field, and we're going to walk through the first couple K groups of interest. So the first one, K0 of R, this is the easiest one to understand in basically every case, right? K0 of R is going to be the integers, and you're supposed to think about this as saying that, every module over a field is free, right? So they're classified by their dimension, and dimension, well, it gives you a natural number. You group complete it, you get the integers, right? So this is K0 of R, and you can get a sort of nice interpretation of what K0 of R is telling you. K1 of R, it becomes a little bit more complicated, but you get a lot more information. So K1 of R is the group of units of the ring. And this is supposed to tell you something about large invertible matrices. The definition of K1 of R, I'll just say it, is you take the infinite general linear group. So these are infinite matrices that are sort of supported on finitely many dimensions, and you take the abelianization of this group. And for a field, this is the group of units, and this is because large invertible matrices essentially are classified by determinant. And you can sort of see that already, right, K0 of fields doesn't distinguish between any fields. If you take K1, you start to be able to distinguish between different fields, but it becomes a bit more complicated. K2, we have the following definition. Well, this is not a definition, but this is a characterization. It's the second homology group of the special linear group of R for n at least 5 with coefficients in the integers. And you can interpret this, right? You can sort of give an interpretation of what this means, but I don't want to. It's sort of complicated, and it's sort of maybe, not that helpful, at least for the purposes of this talk. What I want to sort of say, though, is that there's clearly something really interesting going on here. I mean, built into this is the fact that for n greater than or 5, greater than or equal to 5, these are all the same group, right? So there's a homological stability component to this definition, or this sort of characterization. And you're sort of picking up more interesting arithmetic information about your rings. The cost of this is that this becomes a lot harder to compute, right? So, as the K groups get larger, they contain different sort of arithmetic information about your fields, but they become sort of a little bit more opaque and harder to compute. That's sort of the cost of this. And these are getting harder to define, and this is why, right, Quillen introduced this idea where instead of trying to define these groups algebraically, you should introduce a space, and you should take the homotopy groups, and sort of these should be the K groups that you're working with. All right. So that's the K theory of rings, and I want to talk about how this is related to geometric topology. So sort of classically, K groups end up being the home of several invariants from geometric topology. The invariants actually, right, they predate algebraic K theory by quite a bit of time, but we can sort of work them into this framework of algebraic K theory. And the way that we go about doing this is you start with a space, you take pi1 of the space, you take the fundamental group, and then you can take the group ring on that. So to every space, I've assigned a ring, and then I take the algebraic K theory of the ring, and the invariants live in the K groups of this ring. Throughout the talk, I'm going to assume that the space I have is connected. It's going to make everything look a lot nicer. And it also has some base point, so I'm not going to write the base point, but pi1x, of course, I have some base point here. So I want to talk about a couple of these invariants, mostly because I think they're cool, but also sort of motivates the A theory part of this that we're going to get to. So the two invariants I want to talk about are Wall's finiteness obstruction and Whitehead torsion. So let's talk about Wall's finiteness obstruction first. So the basic question that sort of motivates Wall's finiteness obstruction is I have a CW complex, and I want to know when it's homotopy equivalent to a finite CW complex. Of course, finite CW complexes are sort of much nicer to work with, and you'd like to know when you have this sort of finiteness condition. So we introduce this definition where a space X is finitely dominated if it's a retract of a finite CW complex. And why do we introduce this? Well, it's definitely necessary, right? If X is a finite CW complex, then certainly it's finitely dominated. You could take I and R to be the identity. So certainly, if it is a finite CW complex, you have this, and you can ask, is this actually equivalent to being a finite CW complex? The answer is no, but we know exactly how far it is from being true. So in 1965, Wall introduced this invariant. So if X is a finitely dominated space, there is this class Wx, which lives in the 0th K group of the group ring on pi1x. And it's 0 if and only if X is homotopy equivalent to a finite CW complex. You can compute what this invariant is. I'm not going to define it, but this is a fairly computable invariant using homology. The twiddle here, right, if you notice, it's K0 tilde. This is a quotient of K0, but don't worry exactly about what it is that we're quotienting out by. Okay, so this is the first one, and I think I'm not going to say a whole lot about Wall finiteness obstruction, but I think it's sort of nice, and it's clear that there's something geometric going on here and that you're getting some interesting information. Next, I want to talk about Whitehead torsion, and I want to sort of come at it from the approach of the H-cobordism theorem. So to this, I have to define what an H-cobordism is. So if I have two smooth n manifolds, V and V prime, then a cobordism between them is an n+1 manifold whose boundary is the union of V and V prime. And we say it's an H-cobordism if, moreover, V and V prime are deformation retracts of W. So in particular, V and V prime and W are all homotopy equivalent because you have this deformation retract. And that's what the H stands for. So this is a cobordism with the added hypothesis that you have these deformation retracts, which are giving you, is that Henry Whitehead? I don't know, Doug. I shouldn't say, I'm not sure. Okay. So we have an example, right? For any V, there's a trivial H-cobordism, V cross I from V to itself, right? This is sort of clearly a deformation retract onto either end. And well, for a while, you sort of play around with these, and they're, of course, cobordisms can be hard to draw, and they can be even harder to draw when you sort of add this little extra deformation retract condition here. And so you might ask yourself, like, how bad could these be? And the answer is, well, when V is simply connected, this is basically all you can get, right? So Smale shows that if V is simply connected, then every H-cobordism from V to V prime is diffeomorphic to V cross I. And in fact, the diffeomorphism must fix V. And this is an awesome theorem. And you sort of, most times you would expect that cobordism could get pretty freaky, but when V is simply connected, it turns out that this is not really so bad. Of course, the natural question to ask is, when V is not simply connected, what are we going to be able to say? And this is where K-theory shows up. All right. So when two manifolds are not simply connected, this is going to get more complicated. And to measure how complicated, we introduce an invariant called tau of WVV prime. And this is called the Whitehead torsion. So tau is for torsion. And where does this thing live? It lives in a quotient of K1 of Z pi 1 of V, right? So when V was simply connected, of course, pi 1 of V is the trivial group, and this is K1 of the integers. And the quotient that you do actually just kills this group entirely. So this group is 0. This group being the Whitehead group is the name for the quotient of K1. And the point here is that when the H-cobordism is saying is that, Whitehead torsion is basically vanishing because this group is 0 when pi 1 is 0. So the theorem, which is called the S-cobordism theorem, this is due to Barden, Mazur, and Stallings, says that an H-cobordism is diffeomorphic to V cross I if and only if the torsion vanishes. In particular, and sort of moreover, there's this bijection between diffeomorphism classes in the Whitehead group. So when the Whitehead group vanishes, i.e. when pi1 is 0, there's only one class here. Okay. So the thing about Whitehead torsion and Wall's finiteness obstruction is that you sort of see that these are telling you cool things geometrically about your manifolds, but it's sort of weird that the only thing that you need is pi1. I mean, maybe it's not that weird. The fundamental group is pretty great, but you might ask yourself, like, surely there's sort of more information that could be sort of obtained from V than just the fundamental group, and somehow we should, to get fancier invariants, we're going to need to do something that sort of takes in more than just pi1 of x. So to get fancier invariants, we need to plug something into K-theory that we need to sort of expand our minds a little bit and plug in more than just rings. Okay. So here's a theorem which is deeply imprecise. So given a nice category C, we can form the K-theory spectrum K of C, whose homotopy groups are the K groups of C. So couple things to unpack here. First of all, I've put a lot of names at the top. All the names correspond to a different version of nice category, and the list goes on. What's the sort of general vibe here is that by nice, I really just mean there should be some notion of short exact sequences, right? There should be some way to make sense of short exact sequences in your category, and if you have this, then you can usually define some version of a K-theory spectrum. So for example, you could take an abelian category. These have a perfectly nice notion of exact sequence. You could also take something like spaces, which has cofibration sequences. And you could treat these like exact sequences, and you can feed this into some sort of K-theory machine and spit out a spectrum. And it turns out that this is a really powerful idea. And of course, it recovers the sort of K-theory that we know and love for rings. So in R as a ring, we let CR be the category of finitely generated projective R modules. And basically, this category is nice almost by fiat. If you want to call your category nice, you should probably be able to interpret the category of finitely generated projective R modules in some way, such that the K-theory of that is the K-theory of R. This is like one of the guiding principles here. And a nice sort of bonus is that this lets you define K-theory for ring spectra, right? This is, you can sort of repeat this construction from the last example almost verbatim. Not, of course, absolutely verbatim, but you can sort of copy this sort of idea in spectra. And we have these nice categories of structured ring spectra and modules over them. And this allows you to define K-theory for ring spectra. Okay. But what was the point of this? Where were we going, right? We had the algebraic K-theory of rings, and we wanted it for categories. And the reason that we wanted it for categories is that we wanted to feed in something with a little bit of more geometric flavor and sort of captured more of the geometry of X, so that we could sort of say maybe a little bit more and get some more invariants. So Waldhausen said, okay, well, maybe I can see more about space than just what's in pi1. So we're going to define the following category. X is a space. You're going to take the category of retractive spaces over X. That is the category of spaces which have X as a retract, right? So there's an inclusion of X into Y and a retract back down, Y to X. And I want these to be small in some sense. I don't want to be super precise, but you should think that like Y is really just looking like X with a couple of cells attached, right? Like finitely many cells, and that's sort of the smallness condition that I want on them. If you compare this back to the ring definition, this is the equivalence, right? I need some condition about finitely generated projective R modules, and this smallness condition is supposed to mirror the finite generation condition, right? The point is to avoid something like the Eilenberg swindle. Okay. So you introduce this category of retractive spaces, and oh, sorry, I should say, the A theory of X is the K theory of this category of retractive spaces. And there's this theorem due to Waldhausen, which says that there's this map from A theory of X to the K theory of Z pi 1, which induces an isomorphism on pi 0 and pi 1. In particular, right, A theory of X, I guess, is, a bit more manifestly geometric as an input into a K theory machine. It sort of depends a little bit more heavily or more closely on the geometry of X. And you're supposed to imagine that because you have this map, this is why you have things like Wall's finiteness obstruction living in pi 0 and Whitehead torsion living in pi 1 in K theory of Z pi 1 of X. So this is one way to interpret why those things are living in the K theory of Z pi 1 is this linearization map. But like really, maybe you should think that they lived in A theory the whole time. Okay. We can give a different model for A theory. We can also sort of understand it as the K theory of some ring spectrum that we associate to X. So I'm going to post up here, I'm going to put this proposition, and then I'm going to explain what is going on because there's maybe a lot of symbols here. So on the left, right, we have the A theory of X. That's the K theory of retractive spaces as we've defined it. And then on the right, we do the following thing. So we have X as a space. You take the base loop space on X. This is an associative monoid up to homotopy. Sorry, it's an associative group up to homotopy, right? And if you take the suspension spectrum of that, this becomes an associative ring spectrum, right? This is something like taking the group ring on a group, right? Instead of taking the group ring over the integers, we're taking a group ring over the sphere spectrum. That's what we're supposed to imagine here, right? So, and instead of a group, of course, we have a loop space. We have a group up to homotopy. And it turns out that these are equivalent spectra. And this is maybe surprising if you've never seen it before. You might ask, why are these things related at all? The sort of short and, not entirely precise way to think about this is that if I have a space Y, which lives over X, that should be a homotopy fiber of R. But anyway, so you have a space Y, which lives over X. This is the kind of thing that lives in retractive spaces. And you take the homotopy fiber, this has some homotopy coherent action of loops X, right? So given on the left side, a retractive space, you can produce something that looks like a module over loops X. And that's the kind of input that you would have to the K theory of suspension loops X, right? Or, you should think about if I have a ring, you want to look for modules over loops X, something like this. And this can be upgraded to an equivalence of infinity categories from spaces over X to modules over loops X. If you don't know what that means, don't worry about it. Okay. And the only other thing to say on this slide, right, this is the slide on the spherical group ring model. So what do I mean by spherical group ring? I mean this suspension loops X. And sometimes you denote it by boldface S, adjoin loops X. You're supposed to imagine that this is like the ordinary group ring Z pi 1X, except you've sort of made it more topological in two different ways. The first is that you replace the integers with the sphere spectrum. And the second is that you replaced pi 1 of X with loops X, right? The space whose path components are pi 1X. Okay. So whenever I say spherical group ring, this is sort of what I mean. All right. So we've introduced A theory, and I promised you that this sort of saw more geometric information, so I should tell you exactly how much more it tells you. So here's the theorem, which is known as the stable parametrized H-cobordism theorem, is that there's a splitting of spectra. A theory of X is the suspension of X, wedge WH of X. This is the smooth Whitehead spectrum. And of course, the content here is that the smooth Whitehead spectrum is really interesting, or some of the content here. So what is the Whitehead spectrum? It's a spectrum whose zero space is related to a space of stable H-cobordisms of X, right? So before, right, you would think about here's this collection of H-cobordisms, right? But maybe you could think about, instead of just having a collection of H-cobordisms, you could think about forming a space of H-cobordisms that has path components, which correspond to the diffeomorphism types of these H-cobordisms. But maybe there's more interesting topology going on here, and you can sort of build this into a topological space, right? So one way to sort of think about this is that this is capturing a lot of the sort of H-cobordism information that you can get about X. And essentially, the S-cobordism is some computation of pi 0 of Whitehead X, right? So pi 0 of Whitehead X is supposed to be the Whitehead group of X, which was the computation from the S-cobordism theorem. Okay. So maybe now's an okay time to pause and see if anyone has any questions. All right.
So I have a question.
Uh-huh.
So before you say that a nice category should have some kind of short exact sequences, and so in the category of retract X you introduced before, is there some kind of short exact sequences in that category?
Yeah, that's a good question. I should have said this. So if you think about retractive spaces as, if we ignore the retractive bit for a second and think about them as spaces, you can think about cofibration sequences as your short exact sequences in spaces. And really, we just want our cofibration sequences to live over X now. And this gives you some version of short exact sequences in retractive spaces. Right? So we want them to, the sort of diagrams to commute with the inclusions of X and the retractions back down. Does that make sense?
Okay, yeah, thanks.
Yeah. All right.
Maybe I can just comment that the naming of the Whitehead spectrum has shifted a few times. So there's as stated here, there's sort of a loop space somewhere missing. The Whitehead spectrum, the Escobar-Ism theorem is a computation of pi1 here with this notation.
Okay. Thank you for that. Sorry, I always mix up when this thing is shifted. All right. So I want to sort of shift gears a little bit here now, I think, and we're gonna turn this into an equivariant homotopy theory talk. So I'm gonna give sort of a brief interlude on equivariant homotopy theory because I maybe don't want to assume that you either know what it is or care about it. So recently there's sort of a lot of results that are sort of developing the theory of stable equivariant homotopy theory. And so, what is this? Well, if regular stable homotopy theory is the study of cohomology theories, then equivariant stable homotopy theory is the study of cohomology theories for G spaces, right? Spaces with an action by, say, a finite group G. And so why do we do this? Well, if you spend time moving shapes around, right? You get a lot out of shapes that have symmetries, right? And you'd like to be able to sort of use these symmetries to make your computations easier and sort of encode different information inside of your computations. And algebraically, what does this sort of translate into? This is sort of a vague idea, but it translates into certain operations on your homotopy groups that you can sort of keep track of and use when you want to actually do a computation. So as an example, so this is the sort of thing that you get out of this. So G is going to be the cyclic group of order 2. So I've written a really terrible notation for this presentation of C2. All I mean here is that the generator I'm going to denote by sigma. Of course, it should be sigma mod sigma squared equals 1. The homotopy groups of a C2 spectrum. So this is, you're supposed to imagine this is a spectrum with action by the group C2. And what you get is the following little diagram, right? So I'm going to sort of focus in on what's going on here. At the bottom level here, pi n e of x, you have a abelian group, and it has an action by sigma, right? So it has an action by the group C2, so it's a Z adjoins C2 module. At the top, you have just an abelian group, and we've denoted this by pi n C2. So in general, you're going to have one group for every subgroup of the group G. In this case, there's only 2 because C2 has exactly 2 subgroups, but you might have more. And all of these groups are connected by these sort of operations, which you call R and T. R stands for restriction, and T stands for transfer or trace, sort of depending on how you want to do it. And there's a whole bunch of relations between the R's and the T's that have to be satisfied. I don't want to give the sort of full definition, but the point is that you have, instead of just one group, now you have many groups, and these groups are sort of connected by various operations that you can use. And this thing is called a Mackey functor. And to sort of, if you've never seen Mackey functors before, I want to sort of maybe convince you that this is a useful framework for working in. So let's start with this sort of, hopefully familiar example is that, there are 2 possible extensions of abelian groups from Z2 to Z2, right? You could take A here to be a Z mod 4 or Z mod 2 plus Z mod 2. And of course, if you're doing something with a spectral sequence, you might be interested in resolving which one A is, right? Is A Z mod 2 or is it Z mod 2 plus Z mod 2 or is it Z mod 4? And one way that you can sort of use to resolve these kinds of extensions is to sort of realize, well, maybe I was working with something more than abelian groups. For instance, if you work over F2, there's only one extension because you're working over a field. But another way that you could do this instead of passing to working over a field is you could work over Mackey functors. So here's an exercise. I claim that there's precisely one extension of Mackey functors that looks like this. And the key here is that the top row is exactly the extension problem that I cared about above. And, normally if that was all I gave you, then you can't decide which group A is. But if you knew that it was a part of these Mackey functors, then you could decide what A was, because there's only one extension of Mackey functors that makes this work. So this is the sort of thing that you can use Mackey functors for. Now, of course, you could sort of use ad hoc methods and sort of talk about the transfer and the restriction sort of separately in each example, but Mackey functors and equivariant homotopy theory sort of builds this into the theory, and sort of everything is manifestly functorial. All right. So this is why you want to do equivariant homotopy theory. This is why you want to use Mackey functors. It sort of helps you do these sorts of computation. All right. So the question that we ask then is, can you do equivariant homotopy theory, and can you run the story of A theory, taking into account sort of symmetries or G actions on the space X? So the equivariant A theory spectrum was constructed by Carey Malkiewicz and Mona Merling, denote it AG of X, and it's sort of expected to play the role of A of X in a version of the stable parameterized eCHT Bordism theorem. So what is the status, right? Of course, I say it's expected to play the role or should play the role. So where are we at with this? So for a G-connected space X, there's a fibration sequence that looks like the following. Right, so we have the suspension spectrum of X. We have this AG of X constructed by Malkiewicz and Merling. And then we have something that we're denoting WHG of X, the sort of equivariant Whitehead spectrum of X. And so two things about this. These are exactly the players from the parameterized stable eCHT Bordism theorem before, right? But now instead of having a splitting, we have a fibration sequence. Of course, if you wanted to get a splitting, right, you wanted AG of X to be the product of these two things, then you should show that one of these maps splits. And the other sort of content, which is, of course, very important, is that you want to identify Whitehead of X with something that tells you about stable eCHT Bordisms. And this sort of latter bit, this is ongoing work of Tom Goodwillie, Agusa, Malkiewicz, and Mona Merling. Okay. So the theorem that I want to talk about today is that, right, we can show that this map alpha here from suspension of X to AG of X, we can show that this map splits. And so this is a theorem joint with Maxine Calle, Anish Chedalavada, and Andres Mejia. And the theorem is that the map alpha admits a splitting up to homotopy. In particular, AG of X is split into the product of suspension X and Whitehead X in the equivariant stable homotopy category. This is, of course, more or less expected because it's true in the non-equivariant setting, but proving it is a bit of a chore. And so let's talk about what goes into the proof. So there's two sort of things that we really need for this proof. The two things are the following. First, we want to be able to write AG of X as the K-theory of suspension loops X. We want this sort of spherical group ring model for AG of X. This is not how Malkiewicz and Merling define this spectrum. So this is something that we have to show. And the other thing that we need is we need a version of the equivariant Dennis trace from some version of equivariant K-theory to some version of equivariant THH. Now, I haven't told you what equivariant K-theory and equivariant THH are. I will do that now. So, but I think it's sort of helpful to sort of set the stage by giving a sense of how you're supposed to split this map or how you're supposed to think about the map splitting. So we can sort of, write down what the composite is supposed to be that is supposed to be splitting the inclusion of the suspension of X into the A theory of X. So what is this map supposed to be? The map is supposed to be the following. So let's explain piece by piece what this map is doing. So the first map here, right, is from the A theory of X to the suspension of loops X. This is the spherical group ring model of A theory. This is supposed to be an equivalence. The second one is the Dennis trace, right? I'm supposed to have a map from K theory to topological Hochschild homology, right? You'll notice that the input here, these are the same ring, suspension loops X. The third one here is a computation. You can compute that the THH of the suspension of loops X is the suspension spectrum of the free loop space. right? So the difference between the free loop space and the base loop space is that free loops, I let my loops live anywhere, right? There's sort of no base point restriction condition on where my loops live. And if I have a loop inside of X and I pick a base point inside of S1, then I can evaluate at the base point, and this gives you a map from the loop space of X, the free loop space of X, to X. And if you sort of follow this composite through, you start at A of X and you're supposed to land at the suspension of X. And it turns out that sort of up to homotopy, this is supposed to split this map alpha from suspension of X to A of X. I should say that alpha, the reason we use alpha, this is related to the assembly map. This map is not the assembly map, but it sort of factors through the assembly map. Okay, so the theorem really sort of stated maybe slightly more precisely is that there's equivariant versions of algebraic K-theory and THH for genuine G ring spectra, as well as an equivariant Dennis trace that lets you construct the analogous composite here, and then you can split this inclusion, right? So the real sort of technical labor is in showing basically that you can build these theories of algebraic K-theory and THH, and that you have this Dennis trace here. Okay. So what do I mean by equivariant algebraic K-theory? So I want to start by sort of talking about what sort of already exists and is fairly well known in the literature. So if E is a ring spectrum or a nice category that has some action by a group G, then Mona Merling and Clark Barwick have sort of given us a way to build a genuine G spectrum called KG overline of E. The overline is here because I'm never going to use this one again, and I don't want to sort of confuse it with KG of things going forward. Why am I never going to use it again is because it doesn't do the thing that I want it to do, right? So the sort of thing you might guess is that, okay, well, I have an equivariant algebraic K-theory. I should apply it to this is the equivariant suspension spectrum of loops X, and I would hope that this would give me a G of X. It turns out that this doesn't work, and right, this actually gives you something else. This gives you something else that is quite interesting. Malkiewicz and Merling call this coarse A theory, but it doesn't end up seeing all the equivariant structure. I believe this is equivalent to something called bivariant A theory, which is due to Williams as well. I think these are the same theory. I think Malkiewicz and Merling show that. So why does this sort of miss out on structure? There's sort of a lot of technical details that go into exactly what is going on here. But in spirit, the point is the following. One of these things, taking this sort of KG overline of E, is sort of the equivalent of saying, well, take the group ring on X and then take its fixed points. And this is not the same thing as saying take the group ring on pi1 of X fixed points for various subgroups of H. And it's the one on the right that you really want to do, because the one on the right is sort of capturing a little bit more geometric information about X than the one on the left. Now, this is a bit imprecise, but this is the sort of, this is, I guess, at a very high level, sort of what is going on. The point is that we need a different construction for equivariant A theory if we want to write AG of X as the K theory of some equivariant ring spectrum. So to do this, I need to explain briefly how it is that I'm going to build genuine G spectra. And we're going to use the following theorem. So this is due to Guillaume and also Barwick. So Guillaume do it in the setting of spectrally enriched categories and model categories, and Barwick does it in the setting of infinity categories and stable infinity categories. So the following data determines a genuine G spectrum. For all subgroups of my group, I need a spectrum. So this is not, these are just regular spectra. I need for all H inside of K inside of G, so all chains of subgroups and all little g and g, I need the following maps. So TR from XH to XK, this is called the transfer. I need something called the restriction, XK to XH. And CG, which is the conjugation, because it takes XH to XH conjugate by G. And 3, relations. There's a ton of relations, and I don't want to write them down. But, of course, they can't all be the 0 map, for instance. The transfers need to be, associative in the way that you expect, and the restrictions need to be associative in the way that you expect. And then there's some interplay laws between the transfers, the restrictions, and the conjugations. I should say I'm being fairly imprecise here, right? When I say the following data determines a genuine G spectrum, this is fairly imprecise, but this is the sort of the general sense and how this is supposed to go. How do we do this in practice? Like really, you shouldn't sort of write out these maps. You should build a category, BG, whose objects are the subgroups of G, right? And then morphism sort of encode the maps transfer, restriction, and conjugation, as well as all the relations. And then you should think about this as a functor from BG to spec. If you remember the Mackey functors from before, right, that I was sort of mentioning earlier, this is saying that I should take Mackey functors in spectra, right? These functors are exactly Mackey functors. This category BG, if you take functors from this thing into abelian groups, this is what Mackey functors are. And if you take functors from BG into spectra, the claim is that this is supposed to be equivalent to genuine G spectra. And the sort of imprecision that I was mentioning before is that, like, when I say a functor from BG to spectra, I really mean that this should be the functor B, or the category BG should be enriched in spectra, or it should be an infinity category, and this should be an additive functor from BG into spectra. But I want to sort of avoid these technical details. So anytime I write functor from BG into something, you should be a little skeptical, but you can make it all technically precise. All right, what's the point here? I want to build a G spectrum for equivariant algebraic K-theory. And to do this, I need to build a Mackey functor. Doug asks, can we replace BG by the linear category? BG is the linear category. Yes, this is the category of spans. But it should be a 2 category though. So you should keep track of not just the isomorphism classes of spans, but you should keep track of spans and the maps between the spans. Okay. So I want to build a G spectrum. So I need to build a Mackey functor from BG into spectra. And you can take this a little bit further if you only care about K-theory. What if instead of going straight to spectra, I took a pit stop in nice categories? So instead of building F straight from BG to spectra, I build F from BG into nice categories, and then I extend along K-theory to get to spectra. This is still a Mackey functor. And you can denote the composite by Kg of F. So this is the sort of K-theory construction that I want to use going forward. Again, I should say that there's a lot of technical details here, right? F should be either enriched in permutative categories or, an additive functor of stable infinity categories. This idea to sort of factor things through categories is not due to us. This is an idea, I don't know who it's actually due to, but it appears at least in work of Barwick and also in work of Bowman and Osorno. But the upshot here is that to get equivariant K-theory, you just need to build a Mackey functor in categories or in sufficiently nice categories, and then you can extend along by K-theory to get Kg of F. So let's give some examples here. Let's sort of specialize back in. So let's talk about the sort of Merling and Barwick way of constructing K-theory of G rings. So let G be, or C be a Waldhausen category with G action. Specifically, if you had a ring with G action, the category of finitely generated projective modules over this thing has a G action. Then what do? You should send the subgroup H and G to the homotopy fixed points of the action on C with respect to H. And I claim that this extends to a functor from BG into Waldhausen categories. So in this case, Waldhausen categories is a sufficiently nice category to take K-theory of. That's all you really need to know about it. And this is how you construct the K-theory of G rings. The other one you might be interested in is how you construct AG of X, or at least how Malkiewicz and Merling do it. So let X be a G space. You can consider the category of retractive H spaces over X. So these are spaces with an action of H and a retraction onto X, such that the retraction and the inclusion are maps of H spaces. And the sort of important key here that makes this different from the one above is that you've sort of specified the Waldhausen structure, which is genuine H equivalences between your spaces. Okay. And I claim this also extends to a functor from BG into Waldhausen categories, and you can take K-theory of this, and this gives you AG of X. So how am I going to build a spherical group ring model for equivariant K-theory or equivariant A-theory? So I'm going to start with the genuine G ring spectrum. And for all H, you can restrict the action of G to an action of H. This gives you a new H ring spectrum. And for all of these H ring spectra, you can take, so I've written perf. If you want to just think about these as rings, you can think about these as projective modules, finitely generated projective modules. But you could send H to the category of perfect modules over the restriction from G to H of E. This is a perfectly good category. This is a perfectly good, nice Waldhausen category. And I claim that this actually extends to a functor from BG into Waldhausen categories. We write KG of E for the composite, right? We take BG into Waldhausen categories, hit it with K theory at the end. And the theorem is that if X is connected, then this is an equivalence of genuine G spectra from the spherical group ring to the equivariant A theory of X. And I should say that, right, this construction, of course, this works for genuine G ring spectra. It also works for naive G ring spectra. It works for Tambara functors, green functors, whatever sort of equivariant ring you want to sort of plug in. This is a construction that you can more or less port anywhere. Okay. So this sort of constructs the spherical group ring mono, which is the first thing that I wanted. The next thing I wanted was THH, and I wanted the Dennis trace. But it turns out that this is actually rather easy at this point with sort of all this machinery. Once you have F, you have this functor F from, yes, Jack, that's the answer to your question. So you can build an equivariant version of THH in the same way. So if you have a Mackey functor in nice categories, now here it's very important that I've used quotes for nice. You can't just like take THH of an arbitrary Waldhausen category. But so here, you know, we sort of wrote this out for presentable stable infinity categories. Is what you should interpret nice as, and you should interpret functor as additive, you know, functor of infinity categories. The upshot, though, is that in this sort of exact same way, you can define this THHG of F, which is just done by, you know, applying THH level-wise. And the point is that, well, because the Dennis trace is natural, it's a natural transformation from K theory to THH, you immediately get this trace map from KG to THHG of F. Right. So in fact, the Dennis trace here is sort of coming for free, which is nice because we didn't want to build it again. Okay. So you have K theory, you have THH, and I very briefly want to say something about how do you compute anything with any of these. So for G spectra, right? You know, you're interested in the spectrum and you're interested in its fixed points. And if your G spectrum that you started with was coming from, you know, the suspension spectrum of some G space, there's a really great theorem due to Tom Dieck called the Tom Dieck splitting theorem, which identifies the G fixed points of a space X, sorry, of a suspension, with the following thing on the right. So this is the wedge over conjugacy classes of subgroups H and G. And what do I do? So I have X. X is a space with G action. I take the H fixed points of X, and this has an action by the normalizer of H. This is a, you know, an exercise with sets with group action. And you can take the homotopy orbits of XH with respect to effectively this normalizer group action. And this is really great because it allows you to sort of understand the G fixed points in terms of sort of, you know, geometric data, and, you know, you can sort of work one subgroup at a time, at least for suspension spectra. And it turns out you get a similar splitting on both KG and THHG. So I'm not going to sort of read through what's going on here, but the upshot is that if you take the Tom Dieck splitting and you try to plug this thing into KG or THHG, you get exactly the same splitting, which reduces the computation of these fixed points to ordinary K theory evaluated on loops of X, H fixed points, and then homotopy orbits. So maybe it's a little bit unclear. You should take XH, H, W, G, H, and then take loops of that thing. Right, so loops is happening after the fixed points in the homotopy orbits. And the sort of the point is that you can use these splittings to sort of understand these G fixed points. In the last couple seconds here, I just want to work through one example of the splitting, which I think is really cool. Take X to be a point with trivial G action. Then, of course, loops X is also a point. You add a disjoint base point. This becomes the suspension of S0 with trivial action. It's the equivariant sphere spectrum. If I take the K-theory of the equivariant sphere spectrum, of course, this gives you the K-theory of genuine G spectra. This should be compact objects in the category of genuine G spectra, but whatever. And this is supposed to give me a splitting, and the splitting looks like the K-theory of Borel equivariant spectra for various subgroups of H inside of G. So the K-theory of genuine G spectra has this splitting as the K-theory of Borel G spectra. And I should say this is not due to us. This was already observed by Maxime Ramsey. It maybe predates this, but this is the first place we've seen it. It exists as some notes on his website. But our splitting sort of takes this and sort of generalizes this to more rings than just the sphere spectrum. And with that, I think I'm out of time. So thank you for coming.